Hello again, this is Professor Roman. Welcome back to my lecture series entitled Transition to Advanced Mathematics. So we'll conclude our discussion of proof techniques with a couple of other proofs that I want to do, in particular, we added Bézout's lemma to your toolbox a while ago, and you should be disturbed by the fact that we haven't proven it yet. Because if you're starting to think like mathematicians, you are skeptical. It may seem reasonable, but you need a proof to be absolutely convinced that something is true. Okay. When I'm speaking to somebody and then they say the following is true, the first thing that goes through my mind is, where's the proof? Okay. So, Bézout's lemma. Suppose that A and B are integers whose greatest common divisor is D. Then there exist integers alpha and beta for which D equals alpha A plus beta B. This is the two-integer version of Bézout's lemma. So I invite you to consider the proof when you have n distinct integers. See how you would modify this. This is going to be in some ways, the most complex proof that we've had so far. You can see it runs 3/4 of a page. So it comes over a little bit more over here. So there's some meat in this proof. It's not by any means trivial. This is a proof that if you were to try to construct it yourself, might take some doing, some thought. It's not something you just sit down and do. It might take you a few hours, it might take you a few days. Or you might not hit upon the key idea within a reasonably short period of time, because there's some things going on here. It starts by saying, consider this set. L equals the set of all xa plus yb, where x and y are integers. Okay. This is not a set that came totally out of the blue. We're trying to show that D is, I'm going to call this an integer combination of A and B, because the coefficients are integers. So we're trying to show that the greatest common divisor of A and B is an integer combination of A and B. So it does make sense to look at the set of all integer combinations of A and B and try to show that D belongs to this set. Okay? So that's a reasonable approach. The term integer combination is almost self-explanatory, but if you've never taken linear algebra, you're not familiar with linear combinations, this phrase might be new to you. Let me read you this sentence. To aid the exposition, let us refer to an expression of the form xa plus yb, where x and y are integers, as an integer combination of A and B. Thus, L is the set of all integer combinations of A and B. Oftentimes, what you might consider a temporary definition, that is to say, a term that you're using within the proof only, is a reasonable thing to do. It can indeed aid the exposition to temporarily define some terminology that you use within a proof. But there's two things you should be aware of. One is don't overuse this idea. Okay. And the other is make the definition clear, and a statement like to aid the exposition tells the reader, well, the author's doing this to help me, so that's good. Okay. So our goal is to show that D belongs to L. Well, I guess we need to think about the set L, see what we can learn about it, what properties come to mind. So for example, any common divisor of A and B, so any integer that divides both A and B will divide every every integer combination. If R divides A and R divides B, then R divides XA plus YB. So any common divisor of A and B will divide every member of the set L. In particular, D divides every member of L. Remember what we're trying to show. D is in L. This is a step. Hopefully it's a step forward. Okay? And after all, that implies that D is less than or equal to every member of L. So I guess that's a step forward. Now comes a key idea. As we sit with this, hopefully we will say to ourselves, gee, maybe D is actually the smallest positive member of L. We want to show D is in L. We don't care if it's the smallest positive member, but since it's less than or equal to every member of L, if it's in L, it will be the smallest positive member of L. You have to be a little careful to use the word positive here because there's nothing here about the coefficients being positive, so if an integer is in L, so is its negative. You just replace x by negative x and y by negative y. So we can't say the smallest member of L. There may not be a smallest member. In fact, there isn't a smallest member because you can take x and y. If A and B are positive, for example, you can take x and y to be huge negative numbers. So there's no lower bound. So that's why we're discussing positive members. Perhaps D is actually the smallest positive member of L. When you are trying to construct a proof, one of your best tools is going to be your imagination. And to get the most out of your imagination, you should be constantly asking yourself questions like, what if this is true? Maybe that's true. If only I could show this was true, then I could show something else was true. You have to engage your mind in questioning. Sometimes I refer to it as a wish list. I could have said here, instead of saying perhaps D is actually the smallest positive member of L, I could have said, gee, I wish that I could show that D is the smallest positive member of L. Maybe I can do that. Okay. Well, the first thing to think about once I've said perhaps D is actually the smallest positive member of L is there in fact a smallest positive member in L? In this case, that's not too difficult to deduce because L does contain a positive integer. Since it's non-empty, you can say x and y equal to 1, it does contain something. I didn't say note that L is non-empty, and perhaps I should have. But since L contains something, I can change the signs of x and y appropriately to make sure that to show that L contains a positive element, positive integer. And once I've got a positive integer, I called it p here, then I can just search through the integers 1 through p to find the smallest positive integer that belongs to L. Okay? Here's another remark that would not be included in the proof. When writing a proof, you must be very careful when claiming that something exists to justify that. Sometimes it may be obvious, but what's obvious to one person is not necessarily obvious to another. And this is a case in point. You must, if you're going to say L contains a smallest positive integer, you need to justify that. In this case, it's not terribly difficult, but it's still part of the proof if you are writing a complete, well-designed teaching type proof, or if you're writing a proof that someone else is going to judge you on. Okay. If I was writing upper division, an upper division textbook, I might very well have simply said, note that L is non-empty, and L contains a positive integer, therefore L contains the smallest positive integer. Without, it'd be a little bit shorter than this. Okay. Another idea. So what I've got now is I've got my set L. I'm trying to show D belongs to L. I know that D is less than or equal to every member of L. I know that L has the smallest positive integer, so if D in fact belongs to L, it better be this smallest positive integer, because D is less than or equal to all the members of L. So what I know now is that if this proof is going to work, if indeed D is in L, it must be S. So I need to show that D equals S. Okay. All this discussion we're having here is not just to explain to you this proof, but these are the thoughts that would be going through my mind if I were constructing this proof from scratch. I'd be thinking all the things I'm saying out loud right now. Okay. And this is very helpful because I know now exactly what I have to do. I have to show that D is equal to S. I know that D is less than or equal to S because S belongs to L. So it would be sufficient to show that S was less than or equal to D. Maybe S divides D, something like that. Okay. So what I'm going to do is I'm going to divide the members of L by S. So a typical member of L looks like XA plus YB. And the division algorithm tells me that XA plus YB is equal to QS plus R, quotient remainder. And I can replace S by its integer combination, Q alpha A plus beta B plus R. Remainder is always between 0 and less than S. And I'm going to solve for the remainder, do a little algebra, write it as an integer combination of A and B. So R belongs to L, but R is in this range, 0, less than S, it's the remainder. But S is by definition the smallest positive integer in L. So R better be 0. And so an arbitrary member of L is a multiple of S, which means S, the smallest positive integer, S in L, divides every member of L. So D and S, they both have the property that they divide every member of L. Okay. S is in L, so D divides S, so D is less than or equal to S. What about the reverse inequality? That's all we need to do now to show that D equals S, which tells us that D belongs to L. Well, S divides A and S divides B because A and B are in L, and we've just shown that S divides everything in L. A and B are in L. That's not something I need to elaborate on. I think you can tell. Take x equal 1 and y equals 0. A belongs to L. Okay. So S is a common divisor of both A and B. Whence, that means from where, or from the reason, S is less than or equal to the greatest common divisor of A and B. Okay? S is a common divisor of A and B, whence S is less than or equal to the greatest common divisor of A and B, which is D. So now I have the reverse inequality. I labeled them both, 448 and 449, so I can say, putting 448 and 449 together, we have D equals S. And just as a coup de grace, therefore, that is, D is equal to the greatest common divisor of A and B, that's the definition of D, is equal to S, which is this linear, which is some integer combination of A and B. And that concludes the proof. This is a really good proof to go over several times. It may seem to you right now, I could never have figured this out myself. You don't want to be too harsh on yourself thinking that. It's a perfectly reasonable thing to think, because this proof does have some ideas you have to come up with. It's not just totally straightforward like some of the 3 or 4 line proofs we've done before. There is some meat to this. It's not that counterintuitive. Once you read it, you say, yeah, okay, I guess that's reasonable. So think about this proof. Read it over. If you're really serious about learning to prove things, set the proof aside and try to duplicate it yourself. If you can't do that, which is reasonable, reread the proof, come back an hour later, try to do it again yourself. Once you can do it yourself, you will get a sense of satisfaction out of that. Okay? And you will have learned something. There's a very important corollary to Bézout's lemma that we've also given before. In fact, I think I incorporated this in the original version of Bézout's lemma. 2 positive integers, A and B, are relatively prime if and only if there exist integers alpha and beta for which this integer combination is equal to 1. And I left the proof as an exercise for you. Here's another useful corollary to Bézout's theorem. This corollary is really only a special case. This is not a special case. This is an actual consequence. Let P be a prime number. If A and B are integers, then P divides AB implies P divides A or P divides B. So we may assume that P divides A and AB, but P does not divide A, and show that P does divide B. If you remember, we talked about proving statements that have this form. And we said that one of the best ways to do that is to assume P and the negation of one of these and show then the other one has to hold. So that's what we're doing here. And frankly, in this case, it doesn't matter. Sometimes it'll be easier if we assume not Q. Sometimes it'll be easier if we assume not R. But in this case, we have perfect symmetry between A and B. So it doesn't matter which way we do it. So the moral here is if we assume P divides AB, but P does not divide A, and we are unable to show P divides B, it's not going to help to switch this and assume P divides AB, but P does not divide B, and try to show P divides A. We're going to run into the same problems. So not only may we assume this, but it's the only way we can do this. It doesn't help to swap the roles of A and B here. Since the prime P does not divide A, it follows that P and A are relatively prime. No common factors other than 1, because P has no factors other than 1 in P itself. And as I said once, as soon as you spot two relatively prime integers, you should think of Bézout's lemma, or Bézout's theorem. Actually, this should be Bézout's lemma. Yeah, I did it correctly on the previous page. There is something else known as Bézout's theorem, so be careful there. Therefore, Bézout's lemma implies there are integers alpha and beta for which this integer combination of A and P is equal to 1. What to do? Well, I multiply through by B, I get this equation, but P divides AB, and P certainly divides beta PB, therefore P has to divide B. And that's precisely what we wanted to show.